In this example, we're going to look at a simple magnifier, so a single lens to use to magnify an image, and we're mostly going to use most of the equations we used before. We're going to work in some of these new equations and kind of see how they work in conjunction with our older equations and how the whole thing goes. So the first part of the problem is pretty much like what we've done before in the lens chapter. So what's the position of the image? We do know that the insect is 5 millimeters long, that's H, and placed 10 centimeters from a converging lens, that's P, and a focal length of 12 centimeters, and that's going to be F is equal to plus 12 centimeters because we know it's a converging lens, and converging lenses have a positive focal length. Okay, it's asking us to find the position of the image, which is Q. So we're going to rearrange our lens equation for Q. 1 over Q is equal to 1 over F minus 1 over P. So this is equal to F was 12 centimeters minus 1 over 10 centimeters gives us negative 60 centimeters. This negative sign means that it's a virtual image, that on this lens we have our insect antennae, right? Our insect is 10 centimeters from the lens, and the image is farther back at 60 centimeters, but it's on the same side of the lens. Okay, now we want to find the magnification. We know it's on the same side of the lens, so we know P and Q now. We want to find H prime is what is our H value. So we rearrange the equation. H primed is then equal to negative Q over P times H. Q again is negative 60 centimeters, and we have negative out here, and then 10 centimeters times our original height is 5 millimeters. We get an answer of 30.00 millimeters positive. Now this is a positive H, so this is up, right? And we could figure out what the magnification is going to be 30 over 5, so this is going to be a 6x magnification. So it's 6 times farther back, but 6 times bigger, and it's going to be a virtual image, which means it's going to be upright behind the lens. So since we know Q is equal to negative 60, and the magnification is positive, we know it's upright because H primed is positive, and we know the image is virtual because Q is negative. And then what's the magnification of the lens if the lens is close to the eye? Now what this is part of the problem is saying, what's the magnification of the lens close to the eye? What this part of the problem is saying is we're going to use this magnification equation where we're going to say that the distance between the eye and the lens is 25 centimeters. We showed you the derivation for this equation before, so we're just going to use it now. M is equal to 1 plus 25 centimeters over the focal length was 12 centimeters, gives me 3.08 as the magnification. So this assumes that the image is at the near point of the eye for this to be true. So what does this mean is that if we had taken our equations, and here we said that the image is going to be at negative 25 centimeters for Q, and we solve for P, then the object must be 8.1 centimeters behind the lens instead of 10 centimeters, and we get the very same magnification. So I'm not a huge fan of these equations because they bring into a lot of assumptions. Why can't we just say that we're 25 centimeters? So they are technically an easier equation to use, but I think overall they make everything a little bit more confusing.